welcome to the EE-371 electromagnetic field theory class. I am Dr. Arbab Abdul Rahim from the Faculty of Electrical Engineering. So we were discussing the chapter number 7, that is the steady magnetic field, and in there we have discussed so far two topics, the Biot-Savart law and the Ampere Circuit Law. So the Biot-Savart law we have used for the definition of the magnetic field intensity, what the magnetic field itself is, how you define the magnetic field intensity, or how you compute the magnetic field intensity due to DC current carrying filament. After that we discussed the Ampere's law. The significance of the Ampere's law was that it is easier to compute the magnetic field intensity at a point compared to using the Biot-Savart law to obtain the magnetic field intensity. In today's class we will discuss another very important operator for the vector analysis, and that is called as the curl. So we will discuss the curl today. First we will derive the mathematical expression for the curl, and then we will discuss the significance of the curl and its effect. So going back to the Gauss's law, what we did was that we applied the Gauss's law to the differential volume element to derive the divergence theorem. And that divergence theorem stated that closed surface integral of the electric flux density, this is equal to the volume integral of the divergence of the electric flux density. So in the case of the divergence theorem, what we do is that we relate the closed surface integral to the volume integral, and we obtained this relation by applying the Gauss's law to the differential volume element. Now to obtain the relation for the curl and discuss the curl, so we consider a closed path, incremental closed path having the length of the sides as delta x and delta y in the Cartesian coordinate system, and we assume some current that generates or produce the a reference value of the magnetic field intensity at the center of this closed path. And we say that the coordinates of the center is, let's say, x and y. So this is the closed path around which we will apply the Ampere Circuit Law and will obtain some important relations. Now apply the Ampere Circuit Law to this closed path. To apply this law, what we have done is that this closed path must satisfy two conditions which were necessary for choosing a closed path using the Ampere Circuit Law. What were those two conditions? The first one was that the magnetic field intensity must be tangential. It must be tangential, or it must be perpendicular to the path. So the magnetic field intensity must be perpendicular, or it must be tangential to this path. Now according to the Ampere Circuit Law, if you have a closed line integral, this is your Ampere Circuit Law. It says that the closed line integral of the magnetic field intensity will always be equal to the current enclosed by this closed path. Now if the h is perpendicular to the path, and when h is tangential to this path, what it becomes, this dot product becomes just the multiplication of the magnitude of this vector quantity. The second condition for this closed path was that this h must be constant over the path, or over the parameter. Remember, this closed path is in the xy plane. If I draw this again in the xy plane, so this closed path is in the xy plane. It means it is in the z equals to 0 plane, and these 2 points, as the center is x and y, we have mentioned this as the center, then consider this closed path divided into 4 different paths. Consider this as path 1, this as path 2, this as path 3, and this as path 4, and we move counterclockwise. So this path is having the y can change over this path, whereas it has a fixed value. If this is the x-axis, then this is the x plus delta x by 2, because this distance is delta x. This is x minus delta x by 2. So the center is x. This whole distance is delta x, so this coordinate is at the path 3 is at x minus delta x by 2, whereas path 1 is at x plus delta x by 2. Whereas the path 4, this is at y minus delta y by 2, whereas this path, this is at y plus delta y by 2. Now apply this Ampere Circuit Law to this parameter. How we do this? We say that this closed surface integral, or sorry, this closed line integral, this will be equal to the integral of the first path, that is the dot product of the magnetic field intensity and path 1. Similarly, the magnetic field intensity at part 2 will be delta L2, and the Ampere Circuit Law at path 3 will generate this. Similarly, we will have for the path 4. So this is what we have to solve. Now coming to the path lengths. So if we talk about the path 1, so in the path 1 what we have is the delta L1. So delta L1 is equal to what? This path which is at x plus delta x by 2. So at x plus delta x by 2 we have a path which is having a magnitude as well as a direction. The magnitude of this path is, let's say, delta Ly. The change in y is the magnitude of this path, and the direction is along the positive y direction. It's you can see that this is pointing in the positive y direction, so that's why we take it as the ay. Whereas if we consider the path 3, which is the path 3 is at x minus delta x by 2, this path 3, this is at x minus delta x by 2. Now in this case, let's apply the Ampere Circuit Law. What does the Ampere Circuit Law says? That the h dot dl1, this will be equal to, as the h is having 3 components, the x ax plus hy ay plus hz az. You take the dot product with the length vector, the side vector, which is the delta y ay. Now, which component of the magnetic field intensity will be along this path? We can answer this using the concept of the conditions required for the selection of the path. What are those conditions? The component of the magnetic field intensity which is tangential to this path will be present here. And what is that tangential component? It is the hy. This hy component is only tangential to this y, and even if you solve this dot product, you will again obtain only the hy component of the magnetic field intensity. So either you solve this dot product, or you use the concept of the tangential component. You must have this concept. The tangential component of the magnetic field intensity will be present, because so this expression becomes the hy, and this magnetic field intensity component is at the coordinates. At which coordinates this magnetic field intensity is? At the del x plus delta x by 2 and y. We are not taking z here because the z is 0. This is because we see that the path is in the xy plane or in the z equals to 0 plane. So we'll not have any we are not discussing, or we are not taking the z as the coordinate into the del y. So this is what we will obtain for the path 1. Now for the path 3, what we have, first you have to write the path 3. It is having the magnitude, again the magnitude is delta y. This path is having a magnitude which is change in y. The x is not changing, only the y is changing. So this is having a magnitude delta y. This must be some length, and this is in the direction of negative y. So this negative sign, this is because of the negative y direction. You can see here is that this length is in the y negative y direction. Then this expression h dot delta L3, here again using the same explanation, we can see that we will have only the y component of the field, and this y component of the field is having some coordinates, which is my x minus delta x by 2 y. This is delta y, and the minus sign due to this length. So this is what we have, the h dot dl1 at path 1, h dot dl3 that is for path 3. Now let's add these intensities, as we will add all these at the end. So let's add the intensity from path 1 and path 3. Now adding the intensities of path 1 and 3, what we have is what we obtain is, we obtain h x plus delta x by 2 having these coordinates delta y minus the only having the y component. So this is x minus delta x by 2 y into the delta y. So we can take the delta y common, and we can write this as the hy x plus delta x by 2 y minus hy x minus delta x by 2 y, take the delta y common. Now to revive your concept of the partial differentials, I hope that you know this, that the partial differential of the y component of this with respect to x, this is equal to the h component h x plus delta x by 2 where minus the h x minus delta x by 2 y divided by delta x. This is basically the definition of the partial derivative. Now if we compare this, we can say that the h x plus delta x by 2 y minus h x minus delta x by 2 y, this is equal to partial hy or partial x into the delta x. Now replacing this term by this partial hy or partial x, which comes out to be h dot dl equals to, remember this is only for path 1 and 3, this addition is through path 1 and 3, then we will have to add the path 2 as well as the path 4, but this is for the path 3 only. So I can replace this by the partial hy or partial x delta y into delta x. So instead of this these terms, I have put this term. So this is what we obtain. Remember, what is this delta y and delta x? We will explain this later on also. This delta y and delta x, this is basically the area of the path. The one side is delta x, the other side is delta y. So the delta x or delta into delta y of this rectangular path, it gives you the area of that path. Now similarly, we can perform this for the path 2 and path 4. How we do this, you already know that. First I will just give you the some hints, that is the delta L2. First you have to locate the delta L2. So the delta L2 is, you can see here that this delta L2, or the second path, this is the second path. The second path is at a fixed value of y, that is y plus delta y, and it is having the magnitude which is delta x. So this path is changing only in the x direction, having the magnitude delta x, and it is having the direction which is negative ax, because the x is, the positive x is in this direction, and this path is directed in the opposite x-axis. That's why we take this as the negative x-axis or the minus ax. So the path will become as the delta x, the magnitude, and the direction is the minus ax. Similarly, the delta L4 or the path 4 is having the direction as the ax and the magnitude as again the delta x. Remember, this delta L2 is at y plus delta y2, and this is at a fixed y coordinate, that is the y minus delta y by 2. So from this again we will obtain, this is what we have obtained from the path 2 and path 3. Let's call this as a, from the addition of the part 2 and 4 we will obtain the h dot dl from paths 2 and 4. The addition of part 2 and 4, we obtain the minus hx over the y into the delta x and delta y. So this is what we obtain for the path 2 and 4. Now we can go back to our expression in which we want to obtain the closed surface integral of the h dot dl, which we said this will be equal to the path 1 plus path 2 plus path 3 and path 4. So the path 1 and 3 is given by the partial hy over the partial x, delta y, whereas the 2 and 4, this will add up to minus partial hx or partial y into delta x and delta y. If we take this common, what we will obtain, we will have hy over hx minus hx over y into this area. This is, remember, this is the small area. Let's call this as delta s, this area as this delta s. So this is what we have obtained so far. So we have obtained this important relationship, the h dot dl equals to the partial hy over partial x minus the partial hx over the partial y into the delta s. This relation we have obtained by applying the Ampere's circuit law to this path. Now what we have obtained is an important relationship giving you the current density. How? Let's see. So this expression we can rewrite as the integral h dot dl over the area of the path. This we can write this as equal to the minus partial x partial y. This is partial x. This is what we can write. Now what is this h dot dl? According to the Ampere's circuit law, the closed line integral is always equal to the current enclosed by that path. So this is equal to the I. Now if we divide this both sides by the area, this becomes the amperes per meter square, which is basically the current density. Now as we shrink this surface area, it means that we limit this delta s tends to 0, if we shrink this surface area, this becomes the current density, exactly equal to the current density, and this current density is along the z direction, because we have said that the path is in the xy plane, so the current crossing this xy plane is basically the z component of the current density, which is now equal to the hy over x minus hx over the y. And precisely if we represent this as a vector quantity, so then this is the magnitude of this current density in the z direction, because we have said that we have the path in the xy plane and the current passing through this surface is along the z direction, because the current is always parallel. In this case, the current is always parallel to the unit vector of this area, and the unit vector of any path, you already know, we know that this is always perpendicular to this path. So the perpendicular to the xy plane is the z direction, and that's why we say this is the z component of the current. Now if we choose closed paths oriented perpendicularly to each of the other two coordinate axes, we will obtain the other components of the current. That is, it means we will consider a yz plane which is perpendicular to the x component of the current, and using the same procedure we will obtain the x component of the current, which is the partial hz or partial y minus the partial hy or partial z in the x direction. Similarly, in the y direction we will have partial hx or partial z minus partial hz or partial x. This is along the z direction, so the total current density we can write as J equals to J, the component along the x direction, component along the y direction, plus the component along the z direction, which I can write as the x component is the partial hz or partial y minus partial hy or the partial z. This is along the x direction. Similarly, I can rearrange this as the partial hz or the partial x minus the partial hx or the partial z. This is along the y direction. I have just taken the minus common from here, and the z component is we have obtained, that is partial hy or the partial x minus partial hx or the partial y. This is along the z direction. Now let's call this expression as expression 1, and we go back to our chapter number 1, that where we discussed the cross product. So the cross product, we discussed first the del operator, and then we take the cross product of the del operator with the magnetic field intensity. So the del operator we have discussed before, that this is equal to the partial by partial x, the ax, plus the partial by partial y, ay, plus the partial by partial z, az. This is your del operator. If you take the cross product of this del operator with the H field, which is having three components in the Cartesian coordinate system, that is the x component, the y component, and the z component. Now if you take the cross product, for the cross product we have discussed a straightforward technique, which was that we will take the determinant of this product as partial by partial x, partial by partial y, and partial by partial z. This is the hx component, the hy component, and the hz component. So we have discussed this before, that how would you take the cross product of the two vectors. The cross product of the two vectors we can obtain using this procedure, this determinant, this is basically the unit vectors, and the under the x direction we write the x component of both vectors. In the y column we write the y components of each vector, and so on. Now you take the determinant. If you open this determinant, what you will obtain is, you will allow, first you have to multiply the partial by partial y, the hz minus the partial hy over the partial z. This is along the x direction, minus the partial hz over partial x minus the partial hx over the partial z. This is along the y direction. Similarly, the partial hy over the partial x minus the partial hx over the partial y. This is along the z direction. So now if you look at expression number 1 and you look at this expression number 2, which is the cross product of the magnetic field intensity. So the cross product of the magnetic field intensity, this and this expression, they are exactly the same. So we can see this, that this current density, this is equal to the cross product of the del operator and the magnetic field intensity, and we call this delta cross operator as the curl operator. And we obtain this important relationship, which is, if you apply the curl to the magnetic field intensity, this will give you the current density. So the curl is basically the rotation of the magnetic field intensity. So you can see here is that we are rotating or circulating through a closed path. So this curl of the magnetic field intensity gives you the current density, and this is, by the way, your third Maxwell equation, and we can write this as the curl of H also, which is equal to the J. So from here we have obtained our very important parameter or the operator, which is called as the curl. So if you apply the curl, or the curl gives you the rotation of the field, so the rotation of the magnetic field gives you the current, and we call this as the third Maxwell equation. The first Maxwell equation we obtained by using the or through the divergence, and that was that the divergence of the electric flux density, this is always equal to the charge enclosed by that closed surface. This was the divergence theorem. Now what did it say? Just a quick reminder. The divergence says, this del dot D says that the what amount of flux lines, we measure the flux lines entering and leaving this surface. If the number of flux lines entering the closed surface are greater than the number of flux lines leaving this closed surface, we say that this divergence is negative. It means it is acting as a sink. If the divergence, the number of flux lines going out are more than the number of flux lines going in, we say that the divergence is positive, or there is a charge inside, or we have a source inside. Then if the divergence, if both the lines are equal, the number of lines going in equal to the number of lines going out, then the divergence will be 0. It means there is no charge inside that closed surface. So the divergence gives you the charge inside a closed surface, whereas the curl of the magnetic field intensity gives you the current crossing that closed surface or the closed path. So the either curl or this third Maxwell equation which we have derived through the Ampere's law. This is nothing but just the rotation of the magnetic field intensity giving you the current density. So this was the first Maxwell equation, this is the third Maxwell equation, and remember this is the point form of the Ampere Circuit Law. So the curl gives us the point form or the differential form of the Ampere Circuit Law, which was our objective. Now let's apply the same definition of the curl to the electric field intensity. So what was the definition of the curl? Let me rewrite the definition of the curl. That was curl of any vector. This will be equal to the closed path integral of that vector quantity divided by the area. When the area tends to 0, it means that the area becomes very, very small, which is the point form. Now if you replace this the magnetic field intensity by the electric field intensity, what we will obtain is the electric field intensity, the curl applied to the electric field intensity, the closed line integral of the electric field intensity, again divided by the area 0 divided by the area. Now to analyze this closed path integral, what does this mean? If when we talk about the Ampere Circuit Law, we say that we choose a closed path around the source such that the field must be either tangential or perpendicular to the source. Now as we know that the electric flux lines, they are always perpendicular to the surface, so this expression, this becomes 0, this because the E and the path length, they are perpendicular to each other, or this can be explained in some other words also, because the E dot dl is basically the work done. So as you remember, this is the work done which we have described in the previous chapters, and the work done through a closed path is always 0. So this is the work done over the closed path. As we have discussed this, that the work does not depend on the path you choose, it only depends on the initial path and the final path. So in a closed loop, the initial and the final path are the same, so that's why the work done will always be 0. And from here we can say that the curl of electric field intensity is always 0, and this is your second Maxwell equation. Now what does this physically mean? This means that we have no rotation in the electric flux lines. The curl of the electric field intensity is 0, there is no rotation, the curl is 0, the circulation of electric field intensity will give you 0. Now to further consolidate our concepts of the Ampere Circuit Law, the point form of the Ampere Circuit Law, that is the curl of the magnetic field intensity, let's solve an example. Now in this example, that is draw problem 7.4 in the work, we are asked to evaluate the closed line integral of H. So you have to evaluate this closed line integral H over a rectangular path. The path is given to you. So let me rewrite these path expression. The path 1, this is from point 2, 3, 4. The second point is from 4, 3, 4. The third, the 4, 3, 1, and then we have point 4. So 4, that is the 2, 3, 1, and back to it. So these are the vertices of the rectangular path which are given to us. That is, we move from P1 to P2 to P3, then from P3 to P4, and then back from P4 to P1, which makes a closed rectangular path. The magnetic field intensity is also given to us, which is 3Z in the AX direction minus 2 x cube in the AZ direction, amperes per meter. Now what you have to find is, you have to find the closed line integral of this magnetic field intensity over this closed path. So you can see from these points, these coordinates, that the path, the rectangular path that we are considering is in the y equals to 3 plane, or in y equals to constant plane. So let's draw our path which is in the xz plane, or at y equals to 3 plane. So consider this as x, this as z. So the point P1, let's say that this is point P1, which is your 2, 3 and 4. Then you have point P2, this is your point P2, which is 4, 3, 4. So this point is at is equals to 4, this is at is equals to 2, this x equals to 2 and x equals to 4. So the point 1, P1 and P2, they are at the is equals to 4. Let's call this path as our path 1. From point 1 to point 2, the path is called as the path 1. Then from P2 we have P3, which is given to us as the 4, 3, 1. So the x is 4 and the z is 1. So this is equals to 1, let's say z equals to 1 point. Then we have the point 4, which is point 4 is given to us, which is 2, 3 and 1. The x is 2, the y is 3 and the z is 1. And then back to point P1. So this is the path which is given to us. Let's consider this path as path 2, this as the path 3. We always go counterclockwise. This as path 4. So this is the path given to us. Now what we have to find is, we have to find the closed line integral h dot dl for this path. Now the closed line integral, that is the closed line integral h dot dl, this we can find by separately finding the line integral of this path, line integral of this path, line integral of this path, and similarly the fourth one, and add them up. So I can say that the line integral of path 1 is h dot dl1, the line integral of path 2 is h dot dl2, plus the line integral of path 3, which is h dot dl3, and the line integral of path 4, which is h dot dl4. So we have to solve this line integral. We will solve these integrals for each path. Now coming to the path 1. So the path 1 is we will solve the rest of the paths similar to the path 1. In path 1, the integral is h dot dl1 and the path 1. So first of all, what will be the limits of the integration? So if you talk about the path 1, in the path 1 you can see it extends from x equals to 2 to x equals to 4 at a constant z equals to 4 value. So the z is constant here, and the change in length, is only in the x direction, that is, it changes. We will consider the limits according to the direction. So the direction is from point P1 to point P2, so we will choose the limits from point 2 to 4. The x changes from 2 to 4. The z value is constant. It is already constant in y because it is at y equals to 3 plane. So the only variable that is changing is the x. The z is constant. So then we will have the h, which is 3 z a x minus 2x cube a z dot the differential length. So the differential length is changing in the x direction only. That's why we can write this dl1 as the dl1 we can write as the change in x, and this is in the x direction. So that's why we write it like this. Then again we can solve this as we have done previously, that the z dot product of this ax and x, this will give you the 3z dx, and again you can write this directly also, the component of h. So you will see that the component of h, which is only along the direction of the path, is contributing to this line integral. The other components of the h which are not along this path direction are not contributing. So you can directly write if you know the path, the direction of the path, you can take only that component of the h field and consider it as the component of this line integral. Now if you solve this, what we will do is the z is constant, this is path is at z equals to 4, so we'll put the value of z here. The integral will become x in the limits 2 to 4, or if you put the limits, what we will obtain is 24 amperes. So the closed line so the path integral of path 1 gives us 24 amperes. Now we will repeat the same procedure for the other paths also. So for path 2, what we have is the integral of path 2. So the limits of the path 2 are, you can see from here that this path changes only in the z direction, and the limits are from 4 to 1, and the direction is scattered in the limits without giving a separate sign to the unit vector. So if you put the limits from 4 to 1, it automatically captures the negative z direction. So this is in the z direction, and the component along the z direction of this field is only the minus 2x cube. So I am writing this directly. You can use the previous procedure also, but I am writing this directly through the concept of the closed path conditions. So now this is at fixed value of x, and what is the fixed value of x? The constant value, that is 4. So I can write this as minus 2x cube, that x here is 4, and if you solve this integral you will obtain minus 3, so I will obtain 384 amperes. So along path 2 this is 384 amperes. Similarly along path 3 we can have the h dot dl3. The third path is changing from only in the x direction, so the limits are also from 4 to 2. I am taking only the x component of the field, which is 3z. The value of z is constant here. You can see the value of z for this whole path is constant, which is 1. So I can write this as 3 1, and the limits will be minus 2, so this will give me minus 6 amperes. Now for the path 4 I will follow the same procedure, that is the path 4 h dot dl4. This gives you the limits are from z equals to 1 to z equals to 4, and this, as the path is changing only in the z direction, so the component of h which is parallel to the z is only the minus 2x cube. So I'm just writing that component of the magnetic field intensity which is tangential to this path, which is minus 2x cube. Now if you solve this minus 2, the component of the x here is 2, which is a constant, and from this integral we will obtain 3, which comes out to be minus 48 amperes. So now I have to put the values, these values in this expression. Now I have the path integral of 1, I have found the path integral of path 2, similarly I have the values for path 3, and I have the values for path 4. So from this expression I can write this as the closed line integral h dot dl. This is equal to the value from path 1, which is 24, the value from path 2, which is 384, the value from path 3 is minus 6, the value from path 4 is minus 48. So the total value, the closed line integral evaluated at this closed path which is given to us. So the closed line integral evaluated at this path with the given magnetic field intensity comes out to be 354 amperes. And this was what we were trying to find. We were trying to evaluate this closed line integral over the parameter that is given to us for the given magnetic field intensity. Now coming to the second part, in the second part it says that you have to determine the quotient of the closed line integral and the area enclosed by the path as an approximation to the curl of h at y. So you know that the curl or the approximation of the curl of h at y, this is we have approximated this as the ratio of the closed line integral and the surface area. So the closed line integral we have evaluated. What you have to find is you have to find the area, and this will give you the quotient of the closed line integral and the area enclosed. Now the closed line integral, as I said, that we have obtained in the previous part, in part 1, the delta s, which is the area of the parameter or the path, we can very easily find, because the area of this rectangular path is in the length of one side into the length of the other side. The length of one side is delta z, the other side is delta x. So this delta s is nothing but it's just the delta s equals to delta x into the delta z, so the multiplication of the sides. So let's do this. So in part B you have to find this del cross h y approximation, that is the line integral over the surface area. So the surface area of this path is delta x into delta z. So the x changes from 4 to 2, the z changes from 4 to 1. So this gives you the surface area as 6 meters square. Now putting this in this expression, we already know the value of the closed line integral from the previous part, which was 354 divided by this area, and this gives you 59 amperes per meter square. This is the quotient or the approximation to this curve. Now in the third part it is saying that we have to find the del cross hy at the center of the area. It means you have to find the curl of the magnetic field intensity at the center point. So at the center of the area you have to find the curl of the magnetic field intensity. So for this purpose what you have to do is, first you have to locate this center point, and then you can use the definition of the curl and you will find the curl of the magnetic field intensity at the center. So in part C we have to determine the curl of h at the center of the parameter that is given to us, the rectangle that is given to us. Here in this case the x equals to, this point is x equals to 2, this point is x equals to 4, as we have done this before. This is z equals to 1 and this is z equals to 4. Now what will be the coordinates of the center point? You have to determine this. What will be the coordinates of this certain point? Remember, in the beginning of the question we have been given this, that the this plane is in the xz plane, this is at y equals to constant plane, this is at y equals to 3 plane. So the coordinates of the center will, the y coordinate of the center will be again the same, y equals to 3. What will be the other coordinates? The x, the y, and the z coordinates. What will be those coordinates? So I say that these coordinates will be, x will be equal to 3, the y will be equal to again the same 3, and the z will be equal to 2.5. So the coordinates of the center point will be this. This you have to determine yourself. How we obtain this is very easy. Okay, how we obtain these coordinates from these given coordinates. Anyhow, as we have located this center point, we have to evaluate this delta cross h at the center. So the del cross h, this is equal to the curl of h, this is equal to the x unit vector, the y unit vector, the z unit vector, the partial by partial x, partial by partial y, and partial by partial z. The x component of the vector, the x component of the magnetic field intensity is 3z, the y component is 0, and the x component, the z component is 2x cubed. So you just have to solve this determinant, and you will obtain 6x squared plus 3 in the AY direction. So as we have to evaluate this curl at the center of this parameter, and at the center the value of x is 3, so we obtain this 6x squared, and the final result is 57 amperes per meter square in the AY direction. So this is how we evaluate the curl at the center of this parameter. So to summarize the curl operator, this is the curl operator given in the rectangular coordinate system that we have discussed. Similarly, the curl in the cylindrical coordinate system will be like this, and the curl in the spherical coordinate system will be like this. So we will obtain the curl of the magnetic field intensity if the magnetic field intensity is represented in the cylindrical coordinate system like this, and the curl in the spherical coordinate system if the magnetic field intensity is in the spherical coordinate, represented in the spherical coordinates. We will use this relationship. We are not deriving this relationship, we will just use these relationships, and these relationships will be given to you whenever required. Okay, with this we come to the end of our lecture number 40. I hope you have understood all these basic concepts, the effect and the mathematical expression of the curl, and what does we mean by the curl, what is the effect of the curl. Then we have obtained the Maxwell equations. You must know what these Maxwell equations mean. We have discussed each Maxwell equation through physical phenomena also. We have discussed the divergence, we have discussed the curl. Now thank you very much.